Hello students, I am Dr. Varun Mohan from ABES Engineering College, Ghaziabad. This is the fourth lecture of the lecture series of Unit 3 of Engineering Chemistry, BAS 101 and BAS 102. In the previous sessions, we have discussed about various concepts of electrochemistry and battery. Today, we shall discuss about corrosion. These are the contents of today's lecture. First, we shall define what is corrosion. After that, we shall discuss the cause and units of corrosion. We shall have a discussion on the consequences of corrosion. After that, we shall compare dry corrosion with the wet corrosion. After that, we shall focus on Wagner's theory of corrosion and electrochemical theory of corrosion. At the last, we shall discuss a few questions which have appeared in the previous year's examinations. So let us first define what is corrosion. In our surroundings, we have seen that the iron objects quickly undergo rusting in the rainy season. During the process of rusting, a yellow or brown film deposits on the surface of the iron objects, and slowly they lose their strength and mass. Similarly, the ornaments which are made up of silver undergo tarnishing when exposed to the atmosphere. Both of these examples represent corrosion. So corrosion may be defined as the process of gradual deterioration of a metal from its surface due to the unwanted chemical and electrochemical interaction of the metal with its environment. Corrosion may occur in the metal, in the polymers, and in the ceramics also. But our discussion will be limited to the corrosion in metals. Now the question arises, why does corrosion occur? We know that most of the metals are found in the form of ore. Ores are basically the chemically combined state of the metal, which are thermodynamically stable due to their lower energy content. But once we process these ores through metallurgy to isolate the pure metal, we give a considerable amount of energy. So the pure metal is having higher energy content, and that's why the pure metal is thermodynamically unstable. So it is their natural tendency to return back to their stable state, that is of lower energy. They return to the combined state by the oxidation process when those are exposed to the atmosphere, and this process is called corrosion. So corrosion can be understood as the reverse of the metallurgical process. Now we shall discuss about the units of corrosion. The corrosion rate can be expressed in several units. The first unit is mils per year. It is defined as the mils of metal corroded by the environment in 1 year, where 1 mil is equal to 1000 inch. The mils per year is equivalent to 534 W upon DAT. Mils per year is equal to 534 W upon DAT, where W represents the weight loss in milligram, B is the density of metal in gram per centimeter cube. A represents the area in square inch, and T represents the time in hours. So it is time in hours. The second unit in which corrosion can be expressed is milligram per decimeter square per day. So it is milligram per decimeter square per day. Milligram per decimeter square per day. So it is written as MDT. So it is defined as the milligram of metal lost from a sample of 1 decimeter square area per day. Now we shall discuss about the consequences of corrosion. Because of corrosion, the metallic parts lose their strength, so it is the waste of metallic material. Due to corrosion, machines do not work with full efficiency, so it causes the decrease in the efficiency of machines. Frequent replacement of corroded parts cause loss of money, so this is causing the economic loss. Unpredictable machine failures may lead to the risk to life. Leakage of inflammable gases and toxic products from corroded pipelines may lead to fire accidents and health hazards. And corrosion may also lead to contamination of potable water and degradation of the environment. Hence, it is clear that prevention of corrosion is utmost necessary. And for this, we should understand the mechanism through which corrosion occurs. On the basis of mechanism, corrosion may be of two types. The first one is called dry corrosion. It is also called chemical corrosion. It is the simplest type of corrosion. This type of corrosion occurs when metal surface comes in direct contact with the atmospheric gases such as oxygen, halogens, nitrogen, hydrogen sulfide, or with anhydrous inorganic liquids at elevated temperature in the absence of moisture. Because this type of corrosion occurs in the absence of moisture, that's why it is called dry corrosion. Next type is called the wet corrosion. It is also called electrochemical corrosion. It takes place due to the flow of electrons from metal anodic area towards the cathodic area through a conducting solution. So before understanding the reactions involved in the mechanism, let us compare the dry and wet corrosion in more detail. So as we have discussed, dry corrosion occurs under dry conditions. It means absence of moisture. Absence of moisture. Whereas the wet corrosion occurs when moisture is present. So moisture should be present here. Moisture present. Dry corrosion occurs through direct chemical attack of the gases. So it occurs through direct chemical attack, whereas the wet corrosion occurs through the electrochemical attack. Dry corrosion may occur on both kind of surfaces. Those may be homogeneous or heterogeneous surfaces. So it involves both kind of surfaces. Homogeneous or heterogeneous surfaces. Whereas wet corrosion occurs only on the heterogeneous metal surfaces. In dry corrosion, corrosion is uniform, whereas in wet corrosion, corrosion is not uniform. Here in wet corrosion, corrosion occurs only in some areas which are behaving like anode. Dry corrosion is a slow process, whereas wet corrosion is a fast process. In the dry corrosion, corrosion products accumulate at the corrosion site. So corrosion products here accumulate at the corrosion site. Whereas in wet corrosion, the corrosion occurs at the anode and the products deposit at cathode. So here corrosion occurs at anode and the products corrosion products deposit at cathode. Now we shall discuss the dry corrosion in more detail. So this is the overall classification. Corrosion is of two kinds: dry corrosion, which is happening in the absence of moisture, and the wet corrosion, which happens in the presence of moisture. The dry corrosion is further of three kinds: oxidation corrosion, which happens in the presence of oxygen; corrosion by other gases, when corrosion takes place in presence of other gases apart from the oxygen, like carbon dioxide, nitrogen, hydrogen sulfide, etc., and liquid metal corrosion. So these are the three categories of dry corrosion. Now we shall discuss them one by one. The oxidation corrosion. Oxidation corrosion. The oxidation corrosion takes place by direct action of oxygen on metals. It occurs in the absence of moisture. Oxidation corrosion may occur even at ordinary temperatures For example, alkali metals like lithium, sodium, potassium, and alkaline earth metals like beryllium, calcium, magnesium, these undergo corrosion by the oxidation corrosion process. However, most of the metals react with oxygen at high temperatures. If we see the mechanism of oxidation corrosion, according to Wagner's theory, the oxidation corrosion can be explained in uh, these steps. The first step is the oxidation of metal. So here the metal ion is produced from the metal by the oxidation process. So it is oxidation of metal which occurs at anode. Metal loses some electrons to form the metal cation. Then the next step is that these electrons which are released are transported to the cathode. So flow of electrons to the cathode. In the next step, combination occurs between electrons and the oxidant. Oxidant here is oxygen. So we can write it as combination between electrons and oxidant. So oxygen takes up these electrons to form oxide ion. We have two electrons here and we have n electrons here. So this equation may be multiplied by 2 and this equation may be multiplied by n to balance the number of electrons. And the next step is the formation of metal oxide product by direct chemical interaction. So these metal ions and the oxide ions combine to form metal oxide product, and the net reaction may be shown as, so here we are combining the metal ions and the oxide ions. So the step 4 can be written as formation of metal oxide, and the net reaction may be shown as the metal ions here and the oxide ions combine to form the metal oxide. So this is how metal undergoes oxidation in presence of oxygen. The metal oxide layer here, which is formed, acts like a barrier between the metal and the environment. We can depict it here in the slide as a diagram. So suppose This is the metal, and it is undergoing oxidation. So this is metal layer, metal object, and here it is undergoing oxidation to form the ions. Mn plus and N electrons are ejected. These metal ions diffuse towards the oxide layer. So this is the oxide layer. This is the oxide film. These metal ions and the electrons diffuse towards the oxide film. This is the environment where oxygen takes up these electrons. This oxygen is taking up these electrons. So it is taking the electron to form the oxide ion. These oxide ions also diffuse towards the metal surface. So we can see here, this is the metal which is undergoing oxidation, and it produces the metal cation and electrons. In the environment, oxygen is there, which takes up these electrons to form oxide ions. The metal cations diffuse towards the environment, and the oxide ions diffuse towards the metal surface through this oxide film. So due to comparatively smaller size of metal cation, the outward diffusion of metal ion is much more rapid than the inward diffusion of the oxide ions. So it continues the corrosion process. Now, depending on the oxide film, depending on the nature of the oxide film, the corrosion may be prevented or it may continue. This can be predicted by a rule which is called Pilling-Bedworth rule. Pilling-Bedworth rule states that the smaller the specific volume ratio, greater is the oxidation corrosion. The specific volume ratio may be expressed as the volume of metal oxide divided by the volume of metal. So if the value of this ratio is less than 1, which means the volume of metal oxide, formed is less than the volume of the respective metal, the oxide film will be non-protective. In such cases, the oxide film formed over the metal surface will be porous in nature and corrosion will continue. For example, in alkali and alkaline earth metals like sodium, calcium, and magnesium, the corrosion continues due to the porous nature of the oxide film. On the other hand, if the value of this ratio is equal to 1 or more than 1, the volume of metal oxide will be higher than the volume of metal. In such cases, the metal oxide film will be non-porous and protective in nature. For example, aluminium, chromium, and tungsten develop this kind of protective film and the corrosion is prevented. So here, if this ratio specific volume ratio, if it is lesser than 1, the oxide film is porous. On the other hand, if specific volume ratio is equal to or greater than 1, in that case, oxide film will be non-porous and protective. The second type of the dry corrosion is corrosion by other gases. Corrosion by other gases. Various other gases apart from oxygen, like carbon dioxide, sulfur dioxide, chlorine, hydrogen sulfide, nitrogen. These gases may also have corrosive effect on metals, which depends upon their chemical affinity with the metal. In this case also, the film which is formed with the metal may be protective as well as non-protective. So both kinds of film may be formed here, protective and non-protective. If the film is protective in nature, the corrosion process is retarded. Here we can take an example. In protective film, the corrosion process is retarded. For example, in case of silver, when it reacts with chlorine, it forms silver chloride. The silver chloride forms a film which is protective in nature and hence further corrosion will not take place. So corrosion is retarded here. Another case may be where a metal forms non-protective film. When the film is non-protective, the whole metal will get corroded. For example, in case of tin, here we can take the example of tin. When it reacts with chlorine, it forms SnCl4. Here SnCl4 is volatile, hence the inner layer of tin will be exposed to the chlorine atmosphere and corrosion will be continued. So corrosion here will be continued. The third category of the dry corrosion is liquid metal corrosion. Liquid metal corrosion. When a liquid metal is allowed to flow over solid metal or alloy at high temperatures, it may either cause the dissolution of the metal, the solid metal will get dissolved in the liquid metal, or the penetration of liquid metal may happen into the solid metal. Due to both of these reasons, metal may get weakened. So it may either lead to the dissolution of metal, dissolution of solid metal, or the liquid metal may penetrate into the solid metal. So penetration of liquid metal into the solid metal. Both of these uh, incidents may lead to the weakening of the metal. This is called liquid metal corrosion. For example, in nuclear reactor, sodium metal leads to the corrosion of cadmium and it acts as coolant. Now we shall discuss about the wet corrosion. We shall discuss about the mechanism of wet corrosion. Wet corrosion is also called immersed corrosion. It occurs under wet or moist conditions. Through the formation of large number of galvanic cells. In this type of corrosion, transfer of electron takes place from anodic part of the metal to the cathodic part through a conducting solution, and hence it is also called electrochemical corrosion. So here anodic and cathodic parts develop on the metal surface, anode and cathode. The generation of anode and cathode may be caused by several factors, including the presence of impurities in the metal, so if impurities are present in the metal, they lead to the formation of anodic and cathodic areas. Then uneven surface of the metal may lead to the formation of anode and cathode. And further, the differential aeration in different areas of the metal surface may lead to the formation of anode and cathode. So these are the major factors which cause the formation of anodic and cathodic areas. The electrochemical corrosion occurs through several steps, and these steps can be shown as the step 1. It is the generation of anode and cathode. So separate anodic and cathodic parts develop, which are electrically connected with each other through the conducting medium. Then in the next step, oxidation of the metal occurs, which leads to the formation of metal cations by losing some electrons. So this oxidation process is basically the corrosion, which occurs at the anode. In the next step, the electrons released from the anode move to the cathode. So we can write it here as reduction at cathode. This is occurring at anode. So these electrons which are liberated at anode reach to the cathode and lead to the reduction process. So during this reduction process, non-metallic ions are generated like hydroxide and oxide. And in the last step, these metallic ions and non-metallic ions diffuse towards each other through the conducting medium to form the corrosion product. So here the last step is diffusion. It leads to the formation of corrosion product and it deposits somewhere between the anode and the cathode. Now we shall see the reactions associated with the wet corrosion. First, we can write the reactions which are happening at anode part. So these are called as anodic reactions. At anode metal atoms lose some electron to form the metal cation which pass into the solution. So these metal cations which are generated from the solid metal go into the solution. Thus the metal is destroyed by dissolving and hence corrosion takes place at the anode. Then we can write the cathodic reactions. The electrons which were released at the anodic area lead to the cathodic reaction, which may occur by two methods. The first method is evolution of hydrogen. Evolution of hydrogen. And second method is absorption of oxygen. Now we shall discuss these two methods one by one. First, we shall discuss the evolution of hydrogen method. The hydrogen evolution method of the cathodic reaction takes place in acidic medium and in the absence of oxygen. It generally takes place in such a way that the anodic area here is larger than the cathodic area. So we can understand it with the help of the diagram. Suppose we have an iron object here. So we can write it as iron metal. And some of its surface begins to work as cathode. Rest of the area begins to work as anode. As we have discussed, it happens in the acidic medium. So we can write this solution which is in contact with the metal surface as acidic solution. Now, the anode is responsible for the oxidation of the metal. So the reactions here can be written as iron converting to iron 2 plus and 2 electrons are removed. These 2 electrons are taken up by the H plus ions which are present in the solution. So here the protons take up these 2 electrons to generate the hydrogen gas. So under acidic conditions, the reaction can be written as protons are taking up the electron to form hydrogen gas and it is in acidic condition. In alkaline or neutral aqueous solutions, the reaction can happen as, so if we have alkaline or neutral solution, under these conditions, the reaction can happen as water taking up the electrons, so it generates hydrogen gas and hydroxide ions are generated here. So this is how hydrogen is evolved during the cathodic reaction. Now we shall see another method of cathodic reaction in wet corrosion, that is absorption of oxygen. This type of cathodic reaction takes place in presence of dissolved oxygen. So presence of dissolved oxygen is necessary here. Here also we can understand it with the help of this figure. Suppose we have iron metal here. So this iron metal is always covered with a very thin layer of iron oxide. So this is iron oxide layer. Sometimes this iron oxide layer develops a crack, and that small area where the crack is developed begins to work as anode. So here it is small anode. So if it is anode, the rest of the area where the oxide layer is intact, it works as cathode. When such a kind of metal surface which has developed anode and cathode is in contact with the alkaline or neutral solution, then the anode begins to work. It begins to lose the electrons, and these electrons go to the cathode. So the oxidation is occurring at anode, and the reaction can be shown as these two electrons are taken up by the cathode, and oxygen here in the environment takes up these electrons at the cathode to form the hydroxide ions. So half O2 plus water, it generates hydroxide ions. So the reactions which are occurring at the cathode in presence of dissolved oxygen are it is half, sorry. This is anodic reaction. So at cathode, half O2 plus H2O plus 2 electron converts to 2 hydroxide ions. It is in alkaline or neutral solution. Alkaline or neutral solution. So we have seen the mechanism of wet corrosion, and we have discussed two methods of cathodic reactions. First is by the evolution of hydrogen, and the second is by the absorption of oxygen. Now we shall discuss a few questions which have appeared in the previous year's examinations. What is electrochemical corrosion? Write down the mechanism involved in electrochemical corrosion. Calculate the amount of rust formed by complete rusting of 1 kilogram of iron. Electrochemical corrosion we have recently discussed in the previous slides. It is also called wet corrosion. It occurs in the presence of moisture, and in this kind of corrosion, different galvanic cells set up uh, where cathode and anode are developed on the metal surface. Anode is responsible for oxidation and cathode is responsible for reduction. And this cathodic reaction may occur by two methods: evolution of hydrogen and absorption of oxygen. It has already been discussed in detail in these slides. For calculating the amount of rust formed, we have to first know the molecular weight of Fe2O3.3H2O. So molecular weight of Fe2O3.3H2O can be calculated as 2 multiplied by 56 because it has 2 iron atoms, plus 3 multiplied by 16 because it has 3 oxygen atoms here, plus 3 multiplied by 2 multiplied by 1 plus 16. 2 multiplied by 1 for 2 hydrogen atoms and 16 for the oxygen atom. So we get here as 112 plus 48 plus 3 multiplied by 18. So it is equal to 112 plus 48 plus 54. So it is 214 gram per mole. Now, each molecule of Fe2O3.3H2O has 2 iron atoms, and 2 iron atoms have the mass as 112. So 112 gram of iron is needed to produce 214 gram of rust. So we can write it as 112 gram of iron produces 214 gram of rust. 1 gram of iron will produce 214 divided by 112 gram of rust. And if we have 1 kilogram of iron, so it will be 1000 gram of iron will produce 214 divided by 112 multiplied by 1000 gram of rust. So it comes as 1.91 multiplied by 1000 gram, or we can write it as 1.91 kilogram of rust. The same question has been asked by changing the language here. Discuss the mechanism of electrochemical corrosion of iron with evolution of hydrogen. Here here in the question only the cathodic reaction is asked where evolution of hydrogen is considered. What will happen if a zinc rod is vertically half submerged under water? This portion will be discussed in the next session, where we will discuss the differential aeration corrosion. Briefly explain wet corrosion. Wet corrosion is the same electrochemical corrosion. How corrosion can be prevented by metallic coating and using corrosion inhibitors. Prevention of corrosion will be discussed in the next sessions. Define the term corrosion. This is the first slide we have discussed in this session. Describe the mechanism of electrochemical corrosion with the help of hydrogen evolution and oxygen absorption reactions. Here, in the mechanism of wet corrosion, both kind of cathodic reactions have been asked: hydrogen evolution and oxygen absorption, which have been discussed here. Here we have discussed both of these reactions. This is hydrogen evolution and this is oxygen absorption method. How it can be prevented using sacrificial anodic protection. This portion regarding the prevention of corrosion will be discussed in the next session. Thank you for attending this session.